Hey guys, what's going on? It's me, Mr. V. Today we're going to be learning about the history of the periodic table as we start this unit on periodicity. So what is periodicity? Periodicity is a quality or character being periodic, the tendency to recur at intervals. Basically, it happens in a pattern consistently over and over again. Periodicity. Now this is the periodic table that we first learned about that existed when they believed in the 5 elements: earth, fire, air, water, and ether. Ether being like the air of the gods. Obviously, this wasn't the real table, but these are the components, the elements that they believed to make up the entire world. This is the periodic table we know today. Here's my table. I wish. But it's pretty awesome. So this is what it looks like, the periodic table that we know it as it is now. So on the periodic table, there are about 110 different elements that make up the universe, and it's organized on this table in a simple way. One thing to keep in mind is that we know the elements are different from each other by the number of protons they have, the number of neutrons, and the number of electrons they have, as we've learned in previous units. Here's another visualization of the periodic table of the elements. There's a reason for that old guy being there in the middle. We'll talk about him right now. And you can see kind of an illustration for each of the elements you see here. So before the invention or the creation of the periodic table, the chemistry field was a mess when it came to organizing the elements that we knew about. Really difficult to find any information on these elements. Really impossible to predict anything else about how these elements may interact or react with each other. Until we have this guy here, Dmitry Mendeleev, a Russian in 1869, approximately, who was the first guy to come up with the periodic table, kind of known as the father of the periodic table. So here we are at his Facebook site. Get some information about him. Well, one thing we know about him is he is the first one who started seeing these patterns occur, and he organized the elements by increasing atomic mass. So remember what atomic mass is? That was the weighted average of all the isotopes that exist in nature. So that's the one we use that formula for, the one that it's kind of like calculating your grade. So that number is usually on the periodic table underneath the element symbol. So Mendeleev, when he first created the table, created it in a way that we don't use anymore. It's been outdated. He created it by increasing atomic mass. Now, if you take a look at the periodic table, for the most part, it actually does continue along this pattern with a few exceptions that were corrected later. Here's some photos about him. Now, let's hear what he did. Mendeleev, a Russian scientist, placed these elements in order of increasing atomic mass, increasing atomic weight, and started noticing patterns in their properties and their reactivity. First 7 known elements he put in a row, then put the next 7 and filled in the rest of the table where he thought they belonged based on different properties he saw in common. He was able to leave gaps for elements that had not yet been discovered but that he predicted would be, and he saw patterns that every time an element fell into the same column as another, the reason was because it shared similar chemical properties. So what this allowed him to do was make predictions about those gaps that he had in his table before, and he was able to predict what these unknown elements would be like, what their properties would be, what characteristics they'd have, and when they were found, they matched his predictions. And that's the power of the periodic table, just because of its periodicity, the fact that it does follow, this pattern that repeats, has allowed us to learn so much about the elements that fall into the same group or family. Here's another way some people hypothesize that Mendeleev may have completed his first periodic table. Now, if you look at an element on the periodic table that has 101 protons, what element is that? Of course, we'd be looking for an element that has an atomic number of 101. And interestingly, you'll see it is an element Mendelevium, I guess. And that is named for, of course, Mendeleev. All right, there you see him there. Looks pretty tough. Now, the success of his table and his predictions persuaded most chemists to pretty much accept his table and gave him the credit of being the one who discovered this idea of periodic law. However, there were a couple of issues that remained. One, some elements did not work when they are arranged by atomic mass. And two, there was just no explanation for this chemical periodicity and why it happened. There we have Henry Moseley. Let's visit his Facebook profile. He is from the United Kingdom around 1913. And he came and kind of tweaked the table a little bit by organizing the elements instead by increasing atomic number. Now you remember from a previous unit, atomic number identifies the element by telling us the number of protons present in the nucleus of that atom. Also, you all know that the periodic table today is currently arranged by atomic number, not the atomic mass that Mendeleev first proposed. So, as a result of Moseley's change, the problems that did exist, and not too many, but the few problems that existed in Mendeleev's arrangement have now been resolved. A couple pictures here, so you can see again the atomic number on top is how the periodic table is arranged today, thanks to Moseley, the British guy, and that corrected the change or the mistakes that were made from arranging it in order of atomic mass, which was done by Mendeleev, the Russian guy. So be careful, because of course we do have two last names with the letter M. Mendeleev, the father of the periodic table, and then Moseley, who just kind of came in and fixed it up a little bit. So Mendeleev was credited with being the creator of this idea of periodic law, which states that when you arrange elements in order, and now refined to in order of increasing atomic number, thanks to Moseley, you will start seeing that elements with similar properties appear at regular intervals. They appear periodically. So that takes us now to looking at how the periodic table is organized. Well, what we know about the periodic table, it's an arrangement of the elements in order of atomic number, and it shows how elements with similar properties fall into the same column or group. Now, of course, we know Chuck Norris did destroy the periodic table because he only recognizes the element of surprise, but it has been since recovered, and so all's okay. Now, when we look at the elements going across from left to right, that is a row, and that is called a period in the periodic table. Now, if we look at the vertical columns going up and down, just think of columns like in buildings. That is called a group, or what you will later hear also as a family. Now you can see the groups are numbered from left to right, 1 through 18. And you will see when we talk about a group, we will also often use the name family, referring to these vertical columns that you see colored here in this table below. So one thing you're going to learn is that, or have learned actually, is that elements within a group have similar number of valence electrons. And this is why they have similar chemical properties. Of course, we remember the term valence electrons means the number of electrons in the outermost ring. Of course, group 1 here, circled, would be all similar in chemical reactivity because they all have one valence electron. Now, if we look at the element boron in the periodic table and ask what other elements would have properties similar to that of boron, we would have to look at its group or family. So looking here at the column where boron belongs, we could identify other elements that fall within that exact same column. Those elements are aluminum, gallium, indium, and thallium. All would be similar in their chemical properties to boron because they are in the same group or family. Now, when we look from left to right in the periodic table, these are called periods. You can think of them as energy levels, these rows. They identify the number of energy levels, the number of rings that you find in this atom when drawn in the Bohr model representation. So here we see row 4. This row 4 would have 4 energy levels. Row 6 would have 6. Now here's row 4, would be illustrated as having 4 rings if it has 4 energy levels. Of course, anything in row 6, period 6, would have 6 rings or 6 energy levels, representing the Bohr model. We also see the blocks that we learned about and how you could identify those by looking at the periodic table. Of course, helium kind of moved over to the left to represent the S block. The P block, groups 13 through 18. The D block, groups 3 through 12. And then the F block, the lanthanide and actinide series below. So let's take a look at the main group elements. These are elements of the S and the P block. So anytime we talk about main group, we're referring to these tallest columns, these tallest groups in the periodic table. Groups 1 and 2, and then groups 13 through 18. So just like we said, groups are also called a family. Just like your family, you have similar characteristics, and you have a unique name. So just like this family pictured here, probably all shares the last name, and you can see they clearly share physical properties. Elements will do the same as long as they belong to the same group or family. So let's take a look at the groups and their names. The first group are the alkali metals, but what do you notice about one of those elements there? Well, the first one, hydrogen, is in white. It is not a metal, nor is it part of the alkali metal group. Now, of course, we know the reason it's there, and that's because it has 1 valence electrons like the rest, but of course, hydrogen is a gas, not a metal. A little bit about the alkali metals. They are highly reactive. You'll never find them uncombined in nature as a result. And the metal, when you see them, they're so soft, they're able to be cut through with a butter knife. Lithium, sodium, potassium, these are just a few examples. Here in the picture you see sodium. Look up some videos on YouTube. It's really awesome, to see these react in water. They're stored in a special oil just because that reaction is so explosive. They're so reactive that they can't be stored dry, otherwise they'll contain a lot of moisture and then react. So check out a few videos of things like these alkali metals, different ones being tossed in water. I know the Mythbusters did a couple of videos on that as well. Here you see, kind of an image of the potassium being stored in the oil, and a small example, probably just a tiny sample of a alkali metal being tossed in water. Pretty reactive. The second group, this family, has its own unique last name also. These are the alkaline earth metals, similar to the first group, so be careful there. They're fairly reactive, not as reactive as the alkali metals, but you will never find these uncombined in nature either. Beryllium, magnesium, calcium, these are the minerals that are important for our body. In the middle we have groups 3 through 12. These are called the transition metals. Of course, most of the periodic table we see are the metals, and these kind of are the transition point between the two groups, the main groups. They're less reactive. They're hard, dense metals that are used often in building, jewelry, and coins. And you can see a few examples here: nickel, gold. Others include silver, copper, iron. Mercury, a liquid metal, tungsten, vanadium. You can see different examples. Now most metals, or almost all metals, are going to be silver in color, except copper and gold. Group 17 at the very end are the halogens. Notice we did skip, kind of a few of the groups in the middle. Those don't have any special name. They're just named for the head of the family: the boron group, carbon group, nitrogen group, oxygen group. Kind of boring, but you could, see a little bit about them as well. But group 17 there in brown are the halogens. They have their own special name. They're all gases now on this end of the table. You can see different colors of gases and different samples here. And group 18 are the most noble of them all. These are the noble gases, the ones that everyone on the table looks up to. They're very unreactive, though. They're very stable. That means you will always find them in nature on their own. They don't need to interact with anything else. They're used in neon signs, balloons, and light bulbs. You've looked at some of these before, and you see an example here: helium, neon, argon. They're so unreactive that they're very stable and they're very stagnant. So when Chemistry Cat told a joke to a bunch of noble gases, there was no reaction. Here they are, kind of stuck up and prudish, because they are, of course, the talk of the table, and everyone wants to be like them. Alright, here we have the F block sitting below the rest of the periodic table, as you know, and they kind of are an offshoot of this part right here, sitting right between the S and D blocks of the table. You can see the two elements here representing the name. This first one is where it starts at 57 with lanthanum. So this first row across in that block are called the lanthanides as a result. Down here you see the element actinium, and so the offshoot of this part right here on the table is this branch here, and because of that these are called the actinides. So lanthanides and actinides for this F block portion of the periodic table. Now if we look at the periodic table here, you can see in this light green on the left side of the table you have your metals, and as you can tell, most of the elements on this periodic table are metals. Now these are going to be located to the left and lower parts of the table, including that F block down below, but one thing to note is the left part of the table, while it is all metals, that excludes hydrogen, which of course we know is a non-metal. Here we have a picture of a goldfish, AU for gold. Now these metals tend to lose electrons. They are the electron donors, and because they lose electrons they become more positive and form what we know are to be as cations. And again, cats have pos because they are positively charged. So that's what a cation is, an atom with a positive charge due to the loss of electrons and as a result having more protons. We know from a previous unit talking about homogeneous mixtures that one of those homogeneous mixtures that looks the same is called an alloy, and metals mix with other metals to form alloys. Think of the gold jewelry you are wearing. It looks the same while it's not all one metal though. It's not just gold. There's often other metals mixed in it. Steel, bronze, other things like that are other forms of metals mixed with metals to form alloys. When it comes to the non-metal portion of the table, you see a much smaller portion represented in the top right, kind of in this orangish, peachish color. And these include hydrogen as well as these other non-metals, mostly gases to the right, upper right part of the table. And these non-metals will gain the electrons that the metals give away. And they will gain electrons, making them a negative ion, which we call an anion. An anion, A-N-I-O-N, anion, a negative ion. So that's what we get when nonmetals gain electrons and have more electrons as a result, a negatively charged ion called an anion. Now if we go back real quick, you see sitting in the middle here in light blue, these are the metalloids, and these metalloids are also called semi-metals, semi meaning partly metal. They're found on the table between the metals and the non-metals. They make up that stair step that you see labeled in the periodic table, and you will see some of them are like metals and some of them are like non-metals, kind of exhibiting characteristics of both, like silicon, arsenic, and germanium. These metalloids are exactly in the right spot because they are kind of metal, kind of not metal, so they separate the two groups on the periodic table, as you can see here. So as you see in this image here, we have in yellow, making up most of the table, the metals to the left of that stair step. Of course, you see bordering the stair step are the purple metalloids, but to the right of that in green are your non-metals, including hydrogen over here. All of these are gases and make up a small portion of the table, while we see the metalloids there in the middle along that stair step, as we pointed out. But altogether, metals, non-metals, and metalloids make up what we know to be the current periodic table that we have today. So let's get these elements to unite and form the Avengers. With americium, thorium, Hulk is a mix of hydrogen with some radioactive uranium, and of course iron for Iron Man. Well, this is the periodic table. Hopefully you all learned a lot more and how you could benefit from knowing things on the periodic table and how it all connects nicely. So thank you, Mendeleev. I'll talk to you all soon.